green. Okay, so let's look at the problem. So um, so this is the problem that that we're looking at. I think I have the link in the Discord chat. So basically, this problem, if you have solved TwoSum before, TwoSum is a very introductory problem on Leetcode. I think we can find it and make a comparison. So let's just see. Look for TwoSum. Okay. So yeah. So TwoSum is basically, if you come in, like TwoSum is like one of the first problem that you solve on Leetcode. It's the easy problem. So basically, what TwoSum is that given an array of integers and a target. So we just have to return the indices of the two numbers such that they add up to the target. So for example, in this case, this is the easy version of TwoSum. We are going to solve this today, but let's just take this as an example, since they have the same test case. So let's say we're given an array, so 2, 7, 11, and 15. So we want to return the indices of the array where like the two index where they add up will become to the target. So like for example, in this case, the element in the zero position and the element in the first position, both of them will add up to become 9. So we'll return 0 and 1. So so there are some difference. You can see the array here is not necessarily sorted. So there can be like 3, 2, 4, or like 3, 3. That's not necessarily sorted. And then to get like 6, you just take 2 and then 4 and just add it together. So basically, this is how this is the first TwoSum. But the second edition of TwoSum, it's a bit harder, but it's very similar. It's actually very similar. It's just a little bit harder. Okay, so we can look back at the same test case. Here, there's one different where, like for example, they want us to add 1 to the original index. So for example, the 0th element and the first element, it became the 1 and 2, which is like we just add 1 to the index. But the logic is still the same. We still have to find two number that adds up to the target. So, but if you notice here, all the array are sorted. Okay, the input array is already sorted. So when we say it's already sorted, yeah, I'll talk a little bit about like what it is later. They actually can leverage these properties of it being sorted to actually to do something to make it quick lah. And yeah, so here's the thing. Okay, so basically this is like very easy to understand. So you read the description, right? So it expects us to return to index. So this is what it expects us to return, and then so there we can also assume that every test case that they give will exactly have one solution. So like there will be some questions where, let's say, what about if I have like I have 2, 7, and then 2, 3, 6, 7. Say if I have, what if I have like 2, 3, 6, 7, right? Then I'm looking for the target of 9. Then there's two possible answers here, where one is 1 and the other one is 4, where 2 add up to 7 would be equal to 9. And then the other possible answers. Okay, the other possible answer here is 3 and 6. Okay, because 3 and 6 both add up to 9 as well. But it's given the description that it says the tests are generated such that there is only exactly one solution. So we can not think about these edge cases because it's already mentioned that. Yeah. So here it also says that we may not use the same element twice. So let's say we have 2, we can only use 2 once. We cannot use it twice. So this is the problem that we want to solve. So but there's something that it's quite tricky where it actually what it says is that your solution must use only constant extra space. So actually the main difference the biggest difference between this first TwoSum and the second TwoSum, it's this part. It's where we must use only constant extra space. So what do you mean by constant extra space? It means that our memory complexity in the end, we cannot. It must be O of 1. It must be O of 1 for the extra memory that we try to use. Whereas in this case, the first version of TwoSum, it actually doesn't matter if you want to use like an extra array, you want to use an extra hash map or whatever. You are able to do that because it doesn't have that restriction. But for this question, we are only allowed to use constant extra space. So using constant extra bit space doesn't mean that we cannot use array or vector of some sort. It's just the way that we use it, we cannot populate too much data into it. We have to use it in a constant extra space. So let's just get into it. There's actually few solutions to this problem, and some are quick and some are slow. So, but this most straightforward solution is where, let's say we have 2, 7, 11, 15, right? And my target is actually 9. So the most straightforward solution here is where for each for each for each element like 2, I will just I'll look through the array once, then I'll look through this array again. So like 2, and then I'll just add them up. So 2 plus 7, is it equals 9? Yes. Okay, then I found it. Is 2 plus 11 equals to like 9? No, it's not. Is 2 is 2 plus 15 equals to 9? Not. So let's say if I change this up a bit, I just change it, let's say, to 1 and then 1 3 6 1 3, let's say 5 6 15. Okay, so if we were to apply this solution, our target is still 9. So we'll start from the first element. So okay, I'll start from first element. So I'll compare a equals to 1, and then okay, so b equals to something. Okay, so at the first iteration, let's just say this is first iter. Okay, so at first iteration, I'll compare 1 with 3. Okay, so does 1 and 3 add up to 9? No, I'll continue. So when I continue at the second iteration, I'll still doing like a equals to 1 because I haven't finished it yet. So I'll do like, okay, b equals to 5. Okay, is 1 a plus b equals to 9? No, this is second iter. So I'll keep on going. I'll like just keep on going until I find the correct one. So third, it's still this one, and it's not correct because it doesn't add up to 9. Then 115, it definitely doesn't add up to 9. So I keep on continue to the fifth iter. So now my a is 3, and then my b would be 1. So I'm not sure if we can do this, but I can say but it actually mentioned in the solution. It actually given it mentioned in the problem. It given this condition. So this condition helps us to make things like we can reduce some amount of operations. So what does this condition mean actually? So let's say the numbers dot length. So like this whole array has like 5 elements, right? And then the answer that we want to return, the first index is always smaller than the second index. So we know that for sure. Then the b cannot be smaller than 3 because index 1 must be smaller than index 2. So b cannot be smaller than a. So we can just skip it. So for this part, we can just skip 1. We don't have to do 1. We can do 3 5. We can straight away do 3 5 because of this condition. So 3 5 is 3 5 add up to 9? No. I keep on continue until the sixth iteration. Okay, then I found it 3 and 6. Okay. So okay, does A and B add up to 9? Yes, correct. Then I found the correct solution. Then at here I would just have to return the index of like just have to return the index of like 3 and 6. So in this case, which is 1 plus 1, 1 plus 1, and 3 plus 1. So basically, is that like why 1 plus 1 is because this is 0 element, this is first element, but the question says we want to, yeah, it's actually want to us to return like one index. Okay, it wants us to return like one index, so we have to plus 1. So 1 plus 1 is 2, and 3 plus 1 is. So this is the answer. So this is one solution that we can do. It's actually not very quick. It's quite slow. But let's just implement it first. Then I'll talk about how we can like optimize it to be a faster one. So let's just do it on my terminal here. I'll probably make this bigger. Yeah. Okay. So like we know that we want to return a vector, right? Oh wait, let me see this. That question. Oh no, never mind. Okay, so we know that we want to return a vector. So I can just declare a vector first. So this is vector of integer. Because in the end, remember that what we want to return is we want to return like the element, like the first index. So we put it in a vector. So in order to do this, it's actually a double for. So I'll just do it first. Numbers dot length and I plus plus. And inside here, you can see that it's actually we want to do like how to say, we actually want to like check for all the subsequent element as well. So we need a nested for loop. So you can see why is it like becoming so slow. But because like for the second for loop, we don't have to start at zero because remember the b will never be smaller than a. The b cannot be smaller than a. So we can actually just say j equals to I because we can just start from the same same position. So and also like I think can and then I think the two number cannot be, yeah, it also mentioned that you may not use the same element twice. So we cannot have a condition where it's like 3 3. We cannot have like 3 3 because we cannot use the same element twice. So instead of like doing j equals to I, we actually it's better that we do j equals to I plus one because we are not allowed to use the same element twice. So this will be smaller and length as well, j plus plus. Okay. Then continue here. What we want to do is we want to check if the numbers at index of I plus numbers at index of j, if it is equals to the target. So if it is equal to the target, what we want to do is we just want to do push back the index. So I just want to push back I plus one. And we want to push back um, j plus one. Then in the end, we just return rest. Basically, this is the solution for what I'm mentioning here. So this is actually the solution. So let's test it out. I don't think I need that much braces. Yeah, definitely need this one. Okay, so let's just test this out. Let's just use this 275 or let's say TC1. Okay. Uh, yeah, I think I can do this right if I'm not wrong. Can I? I'm not sure whether if I can compile it this way. Anyway, so let's just do it. I can just print, what is it called? I can just print TwoSum and pass in TC1 and then which is 9. And let's just see if this works. How does TwoSum? Okay, it actually didn't work. I guess it's because it doesn't work that way. Let's just I forgot how I can. I think is it maybe like this? Sure. To search it up. Kind about it. Initialize. Oh yeah, I can just do that. Forgot about that. I don't have to have this whole thing. Yep. Okay, there's something wrong. Let's see what's wrong here. A bunch of errors. Okay. No match for operators. Oh yeah. Okay. My bad. Okay, because the result that we get is a vector, so we cannot straight away just print a vector here in C++. So we can just say result is equal to some TC1 of. Then we can just look through. Position. Um, so this should work. Oh, it's not dot length. My bad. Dot size. Okay, do this. Okay, so yeah, so we get 1 and 2. Is this the answer? Yeah, so this is the answer that we want. So this algorithm actually works. Like this simple algorithm actually does work. So let's just test it for the other test. Say 2, 3, 4, right? So for 2, 3, 4, 2, 3, 4, and target is 6, we actually expect it to return 1 and 3. So let's just see if it's true. Yep, it actually does work, but it's actually quite slow. Let me. I think I have a time. I can time this whole operation. Yeah. Okay. So let's just time this. Then we can have a clearer picture. So let's say let me just change back to the first test case. Then it's easier for us to see to have like a metric for this part. The target is 9. Okay. Um, just make it clearer. So okay, so this is our first like what is it called? This is our first run using this algorithm, which actually not very efficient. We can see that the whole thing executed in 560 milliseconds. We're going to develop like another solution that can make this faster. But I keep hearing things. Is there like a oh yeah, someone talking something. Okay, so we can make like a faster solution actually. So this is actually quite slow. This is actually if we talk in terms of like time complexity, this is over and squared actually. And instead of like remember that we say the memory complexity it actually requires us to use only constant extra space. Where in this case, the constant we are actually using constant extra space because although we have a new vector or another array, but we actually like pop on 2 variable onto it. Like we only put like we know the if we want to be specific, the memory complexity uh is just like O2, and this is time complexity. So, but as you can see, like the memory complexity, we hit the target, but then the time complexity is actually not that good. Like n squared is very slow. We can try to change this up. We just put it on another function so that later we can do a comparison. Say TwoSum is fast. So instead of like in this case, I'll use my favorite method. We're going to use a like 2 point. So it's actually very simple also if we were to use 2 pointer. So I can have like let's say I have left and right pointer. So I just call left equals 0 and right equals to the right one would be the one from like the number stop size -1. So imagine let me just try to say yeah. So imagine we have like this array, right? Maybe I'll do it here easier. I can't zoom it in. But okay. Are you all able to see if I do that? So this case, what does it mean is that let's say we have 2, 7, 11, 15. That is our input. And we have a left pointer. So this is the left pointer. And then this is the right pointer. Like in terms of their position right now. So we start from here. We just converges the list into the middle. Then we know how like what number add up to. So from the left pointer we have 2, right? Then the right pointer we have 15. So let's say we want to find a target of 9. Okay. So at first iteration, I add 2 and 15. Are they correct? Are they the same? So it's not because 2 plus 15 is 17. It's not equal to 9. Then I just converge them. I just converge the right pointer. So I just converge the right pointer to the left side. So I can just do in the next iteration. I can just do this 2, 7, 15, 15. So whereas here is the left point, here is the right point. So target is still 9. So I just check whether 11 plus 2, okay, not equal. Then I just put it back on. I just put like here, okay, okay, left and right. So is 2 and 7 going to be equal? No. So it's not correct. And then, so this is one way that we can do 2 pointer. Then you'll be wondering, then how about, because you can see that the left pointer doesn't then how do we like ensure that what if like 2 and 7 is in the middle? What if we have an input looks like this 2, 7, 11. Yeah. target is still the target is still 9. Okay, here's 15. So we have a left pointer here, and then we have another right pointer here. Then if we were in this case, actually what we can do is we can actually just keep on how to say, we can just keep on like keep doing like the right one. We can keep move right to here, and then move right to here, move right to here. You'll see that it has no solution, right? Like 1 plus 2 not equals 9, and then 2 7 not equals what. So it actually doesn't work that way. But we actually what we can do is we can how to say, like we can try to do it like we can try to like increment them. Wait, let me think about it. Okay, we can actually increment the left pointer to the. Can add it like this. Then for the right pointer, we can just converges them to the middle. So say if essentially like I just like at this point. So let's say okay, let's say L and right now is not right. They're not equal, right? I just converges them to middle, so I can the second iteration I just put this here, and I put this here. So left and right now 2 and 11 is not equal, right? So but then there's just one middle element. So if it's in the middle, I just detect that it's in the middle. So I'll just put the right here. Then essentially we'll have the answer like where the left and right point converges. Then we have so basically this is idea of like using a two pointers method. Um, yeah, let's just implement it out, and then we'll check whether like how fast it is. In terms of like when we compare them lah. When we compare the two of them. So this one, the original one executed in 560 milliseconds. We're going to see like the two pointer one how fast it would be. It actually will be more like more big. It actually has like bigger effect if we have like a how to say we can have like a bigger input. But let's just code this first. So what we can do is we can do while the left is smaller than right, because we know that they will converge somehow, right? So this is our like sort of like a base case lah, but it's actually not. It's just a condition that we check for the loop to continue moving. So we can check if numbers at the left, okay, plus numbers at the right, probably just yeah left, whether if they equals to the target. So if they are equals to the target, then what we'll do is we'll just rest dot push. Basically the same thing. Let me just copy this. Yeah, and then we'll break out of this loop because like we already found the thing, so we just break out of this loop. Else if another condition, else if like numbers like left plus numbers right, if they are smaller than the target, okay, then I'll just do left plus plus. Okay, then else I'll just do right minus minus. Not wrong. Yeah. So so basically this is how we can do like the okay. Let me just leave some comment. So let's make this more visual, like easier to understand visually. So let's say we have this right. In this place now. Okay. Then like this is the left pointer. This is a right pointer. So while left smaller than right, we'll keep on moving. So left is smaller than right. Um so so like left is now 0, right? And then the right would be 0, 1, 2, 3. So the right would be 3. So I'll keep on doing this. So when it go into the first loop, it doesn't match the first condition because 2 plus 15 is not equals to 9. Then I'll go on to the second condition. So I'll check okay whether the sum of them is smaller than the target or bigger than the target. So if 2 plus 15 is smaller than the target, then I'll do left increment. So I'll increment this, and then but then in this case, you notice that 2 plus 15 is 17. It's definitely larger than the target. So I'll just move the right pointer here. It's become R, and then I'll move on. Okay, move on the second iteration. 2 plus 11. 2 plus 11 is 13. So is 13 bigger or smaller than like the target, which is 9? You just write it here. The target is 9. So in this case, like 2 plus 11 is 13, which is definitely larger than 9. So it's larger than 9. So we keep on decrementing the right pointer. So until here, we'll see that we have the like temp converges at the same position. So like 2 and 7 they add up equal to 9. So then we just match this condition. Then we just break out the loop and we just return. Actually, like yeah, you can just break out of the loop and then you just return. So this is how it works. So let's just provide like another case. Let's say we have something like 1, 2, 3, 7, 8, 8, 9, and then the target is still 9. Then just let's just test it again. Okay, so this is the right pointer, this is the pointer, and then so in this case 1 plus 9, 1 plus 9 it's already bigger than 9. Okay, it's 10. 10 is bigger than 9. So we're going to decrement the like right pointer. So in this case I'll go to 8, and then is 1 and 8 equals to 9? Yes, it is. So I'll just like I'll just like just return it. Okay, so basically this is the idea. Let's just test it out and see how much of a performance boost that we have. So I'll just copy this twice. Then instead of using TwoSum, I'll just use TwoSum fast. Let's just run this again. Oh, okay. My bad. I'm using left and right. Okay, not J. Yeah, left and right. Okay. Okay. Interesting results. Interesting result. But in this case, actually, like the okay, let's just run it again to make sure that we're not doing anything. Let me. Okay, I just use the slow version first. Uh, so okay, the benchmark is 658. What about the second? So you can see, okay, yeah, it's actually faster, but it's not really fast by a lot lah. Like the first one, it's executed in 658 milliseconds. The second one is executed in the 630 milliseconds. They produce the same result. It's a bit faster. Like I said, it's actually not that fast because our input size is very small. So if we try to like, let's just try to get like a really big test case. Let's just try something. Let's say we do something uh, something really big, just like uh, okay, then like 3. So maybe you just want to get like the sum of these two. Let's just check or something. Plus, right, this. So let's take this as the target. Uh, 768. 76877. Okay. Let's say this our input and output. Just do this, and then we have 7. So let's just test this again. Let's just use the slow one and see if we compare with the fast one how it compares. So the slow one executes 700. So I expect the fast one to be a little bit more faster. Okay, let's just see. Uh, Somehow I guess the test case is still not big enough. Um, are we? Oh wait, are we testing the correct thing? Wait. Uh, so oh sorry, my bad. I actually uh I'm using the wrong input. Let's do it one more. So this time we should actually see that the slow one be slower. If we do the fast one, it should actually be Yeah, you can see it's more obvious lah. Now that this two pointer method is like 200 milliseconds faster. Even though like in this case it actually doesn't like show how much faster the algorithm is. It's actually much more faster because in this case, if we talk about memory, the time complexity, like I said, like this is O of n squared, because you essentially have to do a lot. But for this case, it's actually just O of n. Like it's a lot faster. It's just that maybe our input size is very small. Let's just put this code into like Leetcode. I think we can get like a even clearer picture over there. So let's just submit this slow one, and then see what it gives us. Wait, oh, it's wait, what? Oh, time limit exceeded. Yeah, because it's too slow, right? It's too slow. I guess it's because that it's too slow, so it wouldn't like work somehow. But if we were to take the second one, I think this would work because this is a lot faster. I guess like it's a medium problem because like it has some time restriction. So maybe this method is just too slow that it doesn't even pass. Um, we'll just pass the fast one. Uh, fast one. Oh, I hate this model stuff. Okay, so let's just test this one. This is the fast solution. Yeah, and as you can see, like it's much more faster. Like it's just 12 milliseconds, whereas the very slow one, it doesn't even pass because it's just too slow. It say time limit exceeded. So there's actually a difference. So like for some platform in Leetcode, there's actually some restriction. If your solution is too slow, it actually will give you like TLE, which is time limit exceeded. But sometimes we have to think about the complexity. We need like a faster solution. So this two pointer method is actually much more faster. Yep. So basically, that's the solution for the problem. I'll pass the time to Kenny. Kenny here. Oh wait. Yeah. No, not Kenny. It's missing. Okay. I'll pass it to missing.
Hi, okay, so share my screen again. Hopefully today you can see my screen now. Yeah, I think I can see my own screen here. Okay. Okay, I've seen some views, so I think that you guys have already entered. Yeah, okay. So today we are going to go into a new topic. Okay. We are doing dynamic programming today. This is just a very simple, like beginner's question for dynamic programming. So this is a jump game. Okay. So what is dynamic programming? Dynamic programming is actually the act of having a big question, not big question, big problem. Okay, for example, I have this big problem. Okay, and it is super difficult to solve because the problem is so big. So what we do is we cut it into smaller sub problems and we solve the sub problems. Okay, so this is the essence of dynamic programming. Okay, so we have a big problem and we cut it into different smaller sub problems and we solve the sub problems. Okay, so let's just read the question first. So you are given an array of numbers, nums, okay, and I'm initially positioned at the array's first index, okay, and then at each element, it represents the max jump length at that position, okay, and I have to return true if I can reach the last index and false otherwise. So let me just get this test case, okay. So for example, today I'm just going to use, I'll use JavaScript today, but it's actually not that much of a difference lah. It's just that I'm practicing my JavaScript now. So we're going to use JavaScript. Okay. So for example, when I'm at this first index, okay, the maximum steps that I can do is 2 steps. So I can either go 1 step here or 2 step here. Okay. So let's say if I go 2 step here, the maximum I can go is 1 step here. So I will go 1 step again. And the maximum I can go is 1 step, so I'll go 1 step again. And I have already reached the last index, so I can return true. Alright? So this is what the question wants. So let's say if I have a test case of this, okay? So here I have 2 steps that I can go in the first index, okay? So I can either go 1 step or 2 step. Okay, so if I go 1 step here, then I can go 3 steps, right? So I can go 1, 2, 3 to the last index, which I can return true. However, if I take 2 steps here, okay, I will end up at this 1, in which I can only go 1 step, and here I can go 0 steps, so I won't be able to reach the end. So I have to find like the combination that I can do to reach the end. But I think because this is just jump game, so I just need to return true or false. I think there are related questions like jump game 2, 3, 4. You can try. So they will probably ask you to return a path. Okay, but here we are just going to return true or false. Okay, so for dynamic programming, what we do is we can just focus on this one. Okay, instead of focusing on all the possibilities, we can focus on one index at a time. Okay, and then we can continue to calculate. So there are 2 approaches to dynamic programming, which I am going to introduce to you. Okay, so the first approach, we call it the top-down. Okay, so top-down is also known as the recursive way. We do it recursively. Okay, the second way is bottoms up. So this is the way that I like to do bottom up, because bottom up is usually more more error-free, I would say. Top down is more error-prone because there's recursive that you may be able, you may end up in an infinite loop or whatnot. So I like to use bottom up. Okay, so it's just iteratively. Okay, and usually using an array of some sort to an array of some sort to record the process. Okay, so since I've mentioned that I like to use bottoms up more, and also bottom up is easier to implement actually in the more complicated questions. So I'm going to go with the bottom up approach first, and if we have time, we can go through the top down approach. Okay, so what does it mean by bottom up? So for example here, right? So top down meaning that, okay, so top down meaning that we can go from the back and we check to the front. That's why it's from the top to the down. Bottoms up is we can go from the front and we check to the back. Okay, so with this bottoms up, since I've mentioned it's iteratively, okay, so what we can do here, okay, I can record this. Let me just take a screenshot of this. Okay. Okay, so let's take this test case as an example. Okay, let's say if we are at this, okay, hold on, let me just move this. Oops. Okay, so let's say I am a person, okay, and I am standing here. Okay, this is before I enter into the array. Okay, so here, it's just the starting point, okay, the starting point. So now when I'm going to this first element here, okay, I can choose to go 1 step or 2 steps, right? Of course, I can also go 0 steps, but that won't help me because the goal of this is to get to the end of the array. Okay, so I can go 1 step or 2 steps. So meaning that I can actually reach this here and here, right? So these 2 indexes are reachable. Okay. So this is the sub problem that we are solving. Instead of trying to fix the whole thing, solve the whole problem, we look at each index and we see which part is reachable. Okay. Then now I come here. Okay, since I know that this part is reachable, I can continue to go from this part. So here I can go to 1 step, 2 steps, or 3 steps. Okay, so next I can reach here, I can reach here, or I can reach here. Alright. So the same time, when I come here, I know that this step is reachable, so I can go from here. Okay, so I can go one step forward. And I can do the same thing. Okay, so do you know what I mean now? Okay, I can check. And now I'm already at the end, which I will return true because I know that it is reachable. Okay, so at each index, I would just find which places are reachable. Okay, so how can I record these reachables? Okay, but until now, I just want to check with y'all, see if you have any questions about the logic. So this is a very important part. Okay, is that we are actually cutting this huge problem into small sub-problems by just checking each index and see which are the next few index that are reachable. Yeah, I think that should be no problem. So this is actually the basis for a lot of the dynamic programming questions. Of course, there are a lot of types of dynamic programming questions. You know, some that, but this is just one of the types that I would say, the more common types. Maybe we can touch on the other types of dynamic programming later. Okay, so with that, what we can do is we can record like these reachable ones, right? We can record it in an array. Okay, so for example here, so in this array, right, I think that I will start with one index extra. Why? Because this extra index is actually my starting point. Okay, so in this test case, we have 5 elements. But in this new array that I've created, we have 6 elements. 1, 2, 3, 4, 5, 6. Okay. And this is the starting point. Okay. So here we are recording if we can reach or not, right? So we can just make this a Boolean array. Okay. And the starting point would be true because we know that we can always start at the starting point one, right? We are already there from the start. So of course that is true. Okay. And from the starting point, it is true. Okay. So here, actually, I think that maybe I don't need this starting point. I can just start from here. Okay, so let me just change that. Later you will see why I can just start from the first element. Doesn't really matter. Because actually for some dynamic programming questions, we need to have an extra index for the starting point, but in this case, we don't need it. So let me explain why we don't need it. Okay. So because if we read this question, right, I am initially positioned at the first index. So I am already starting at the first index. So I know that, okay, this index, this place, right, is reachable. So I'll put it as true. Okay. So let's say now this first element is 2, right? So I can go 1 step or 2 steps. Okay. Remember, these all are initialized as false. Okay, first I'll initialize all of them as false except for the first index. And now here I can go 2 steps, right? So this would be true. And this would be true. Okay. And now I will continue traverse this array. So I see that it's true, meaning that it is reachable. So I can move from here. So I will check again here. Okay, 3. Then I will continue to populate the array. Okay, so this is the DP table we usually call. Okay, so for bottom-up approach, right, we can also call this the tabulation approach. Okay, in this tabulation approach, okay, we are making this DP table and we are populating it. Okay, and the final solution. So according to the question, you want to know if we can reach the last index, right? So we can just return the value of the last DB table, the last element in the DB table. So I can just return this. Okay. Any questions? Yeah, I hope that I'm being clear here. Yeah, let me know if I'm lagging or you need me to repeat. Questions, we can start to do the coding. Okay. So, maybe we can run through the false case. So this one should be really fast also lah. Okay, so let's just go through this now. Okay, 3, 2, 1, 0, 4. So in our DP table, the first one is true, right? And then the rest are false, initially false. Okay. Okay. So first I can go 3 steps. So I can either go 1 step, 2 steps, okay, or 3 steps. Okay. I was at here. So now I move on to the next index here. Since I see that this is already true, okay, meaning that I can already reach here, so I can go from here, right? So I can check here. I can check the value in this original nums array. I can go 2 steps from here. So I can either go 1 step, so I can just set it to true. It's already true, right? So I'll just leave it. Or I can go 2 steps and set it to true, which is already true. Okay, then I will move here. So since this is true, so I can move this. So I can go 1 step from here. So I will populate this next step to be true, which is already true. Then I go to this index, and I see that the value is 0, so I cannot populate any further steps. Okay, and then I go here. So this is false. So meaning that I cannot move from here. And it's also already the last element. So I'll just return false. Okay. So let me just start coding. Maybe by right I should write the pseudocode lah, but I think I've already done enough explaining, so I'll skip the pseudocode. Yeah. Okay. So let's just start. First, I will create the DP table. Okay. So let's call this the DP table. So I can use array from or array fill in JavaScript. So I'm just going to use array from here, and the length would be the length of nums. Okay, and then I will initialize all of them to be false. Okay, so this should be the syntax if I'm not mistaken. We can also use array fill. So I can just initialize array with the length of the nums. With the length of nums, and I will fill them with false. So this should work also, if I'm not mistaken. Okay. So now, since I've already created the DP table, I will look through the DP table, right? Okay, but before doing that, I have to set the first element to be true. Okay, as we know that, we can already reach the first element without any moves. Okay, so DP table at index 0 would be true. Now we can start to look through the DP table. Okay, so but usually in interviews, we don't call this DP table. We would try to make it more descriptive, okay, like jump table or something like that. Okay, so let me just look through. Again, in interviews, we won't usually use I, we can just write index, but you know, nums.length. Oops. So for all these, right, so what we do when we reach a position, we check if it's reachable. If it's reachable, then we can only go from there, right? So we have to check if the current value is reachable first. Okay, so if jump table, oh no, we call this DP table, right? DP table at I is reachable, so it's true. If it is true, then we will only continue to check for the further values. Okay, so for that, we can check from 1 step to the number of steps in that value. Okay, so we can check from j equals to 1 to j smaller than equal to nums at I. J. Is it? No, should be I. Okay, because I is for here. And then I will increment j. So this is checking for the further steps, right? So what I can do here is I can just do DP table at I plus j, right, equal to true. Okay? But one thing I need to take care of is the indexes. Like what if the number here is 5, right? I can go 5 steps from here. Then I will go out of the bounds, right? I will go out of bounds because of the indexes. So I have to check the index value first. Okay, so I can just do if I plus j is less than num length. Right, then only I will set the DP table. Okay, so with this, we are already done with the tabulation method. So at the end, we can just return the last value of the DP table. So DP table at nums.length minus 1, which is the last value of the DP table. Let me see my Discord. So this should work. Let's run this. Can anybody tell me the complexity for this? Difficult. Succeeded. Okay, maybe there's some issue here. Let's try to debug this. Okay, so first I'm setting the first one to be true. Okay, and if this value is true, I will go into this for loop. Okay, where I start with j equals to 1. Oh, so here is j. Right? J is smaller than or equal to num set I. So here I'm basically going through the steps from one step to the value of step that is given in the num array. Okay, let me try to run this again. Okay, let's just submit this and oh no, there's an edge case that I need to take care of. So I think there will be an error. Oh, no errors. Oh, okay. So actually, with the edge case that I've thought of is that maybe that the length of the array is empty, but I guess that the length shouldn't be empty. But if the length is empty, then we can just do a checking beforehand. Okay. How's the complexity for this? The time and space complexity for this solution? Anybody wants to try? It's okay. Then I will just go on and explain this. Okay, so for this, the time complexity is actually O of mn, right? So let me define mn real quick. Okay, m is the length of the nums array. Okay, and then n is the maximum number of steps. Right, because this is like an inner for loop, where this is the length of the number array, and this is the maximum number of steps. Okay, we are getting the maximum because for complexities, we are always thinking of the worst case, right? Okay, and then the space complexity would be O of m plus n, right? But we can just take the larger one, right? Because for complexities, we can always ignore the smaller one. So it's actually just max. We can simplify to max of mn. This would be the time and space complexity. Let me see if I have time to talk about the top-down approach. Okay, we have 6 minutes, so we can speed run this. Any questions? Okay, cool. So, by the way, just if you have any feedback, you can let me know, like how, if this session is helping or whatnot. Okay, so let's try to do a recursive approach. Okay, so to do this recursive approach, first, I think I need to explain the logic first, right, before I start coding. Okay. So recursively, what I can do for a question like this, okay, maybe I can copy this. I'll paste it here. Okay. So recursively, what I can do is I can start from here. Okay, so I can start from here. 2. No, sure, sorry. It should be, okay, so I will use indexes in this tree that I'm about to draw. So this is index 0, 1, 2, 3, 4. Okay, so initially I'm at index 0, okay? And from here I can go to index 1 or index 2, right? Because I can go 2 steps. So I can go to index 1 or index 2. Okay? And then from index 1 here, I can go 3 steps, right? So I can go to index 2, 3, 4. So I can go to index 2, 3, 4. Okay? And then from 2, I can go to 1 index, which is to index 3. Okay, at index 3, I can go 1 step, which is to index 4. So I can use this tree method to find out if I can reach index 4 or not. Okay? So recursively, I can call the next indexes. Okay? I can call for the next few indexes recursively. Okay. So this is just a matter of making a simple DFS tree. Okay? We are doing depth first search here. Okay, so we were just doing like that. Okay, so this is actually still not dynamic programming because we are just doing a simple depth first search. Dynamic program is the optimization that comes later. So I will try to, okay, confirm cannot make it, but I will do it anyways. Okay, so first of all, for a recursive function, I have to have a base case, right? So my base case, I can make it such that if I equal to the last element, okay, then of course I will just return, right? So I will use index. Okay, so maybe I will create like a helper function. Okay, I'll just call this the depth search function. And I will take in the index as a parameter. And if the index is more than, okay, so I have to take in nums as well. You know what, I'll just make this like nested so that I don't have to take in nums. Okay. If index is more than or equal to nums.length minus 1. Okay? So meaning that we have already reached the end. I can also do equal lah. Doesn't really matter because of the implementation that I'm going to do later, which you will see. Okay. So in this case, I will return true because I've already reached the end, right? Okay. Now, let's do one more thing here. So we will go through the indexes. We will go through the values and we will recursively search. Okay. So again, we can just, I'll just copy this. Okay. So this is what we're doing, but instead of I have to use index. Okay, so I will start with, no, I have to start with j equals to 1. Okay, I will start with 1 until nums index, right? So for example, here if the value is 2, then I'll start 1 to 2. If the value is 3, then I'll start 1, 2, 3. So I'll go through the steps, okay? I'll go through the steps and I will recursively search. So I will do depth first search of index plus steps, right? Okay. So for example, if I'm already at index 2 and I want to go 1 step, so I need to, sorry, here is index 1. So if I'm already at index 1 and I need to go 1 step, so I just need to add the steps. Okay, so here is what I'm doing. Okay, so J is actually the steps. Maybe I can make it step, so it will be easier to understand. Okay, I would do this recursively. So what does this mean if it returns true? Meaning that following this path, okay, if it returns true, meaning that, let's say if I'm already here, okay, and I call the function to check the next one and it returns a true. Okay, so if it returns true from here, it means that this path is the correct path, right? This path brings you to the end. Okay, so if this returns a true, okay, so if this returns a true, okay, to be more descriptive, this is what it means lah, but I don't have to put it like that. Okay, if this returns a true, then I can recursively return the true value, right? Okay, so for example, if let me just change the color. Okay, so if I am here, okay, and I call for this number, and I call for this, okay, and I return true up here, right, because I already reached the last index. So I have to return true back to the top, right? So at the top function, I would have the value of true, which I can return at the main function. Okay, so this is what I'm doing. I'm bubbling up the solution. Okay, I'm returning true and bring it back up. Okay, so what happens if I finish this for loop? Okay, if I finish this for loop, it means that I actually go through all of the subtrees, right? And I still cannot find any solution. Because if I find a solution, then I already return true. So what I do after I go through the for loop, I will return false. Okay? And this is the main logic of my sub function. Okay? Then what I can do in my main function is I can just return the first search of index 0. Okay, so why 0? Because we are starting from the top. This is why we call the top-down solution. Okay. So we are starting from the top of the tree, and we are calling right down. Okay. So as we call till the end, if there's a true, then the true will be passed back up, right? So I'm sending this index 0 to start with into this deficit function. Okay. Yeah. So this is basically it. Okay. So let me just try to run this. It won't run the submit because this is actually not dynamic programming. All right. This is actually just tree. So the complexities for this is actually O of m to the power of n. Okay. If we look at, oh sorry, it should be n to the power m then, if we follow this definition. So this is actually just normal tree complexities, okay? If you don't understand, maybe you can read up the complexities for depth search in trees. Okay, so time complexity is n to the power of m. Okay, and then the space complexity is actually log base. Okay, so it should be log base n and then m. Okay, you can go read up why is it how it is. So how can we optimize this to be as good as the tabulation method, which is mn, right? So we can do this using memoization. Okay, so for top down, right, there is this technique called, maybe I'll just put it here, memoization. Okay, this is what it's called. Basically, you remember the repeating subtrees, so you don't have to do it again and again. Okay, so for example here, this tree is already super messy, but if you can see, we have a 3 to 4 here, and we can also have a 3 to 4 here, right? If I know that 3 leads to 4, right, from here, if I already know 3 leads to 4, which is a correct, which returns a true, okay, basically, then here I don't have to go down. I can straight away return true here. So I don't have to go this extra step. So in this graph, I'm only saving one step, right? No big deal. But in some scenarios, you'll be saving like a whole subtrees of steps, okay? By just remembering that this actually returns true. Okay, so this is what we call memoization. And to do memoization, we can use a hash map. Yay! But the thing with JavaScript is that JavaScript doesn't have a hash map implementation, so I'm just going to use map. Yeah, I'm talking quicker and quicker here because we're already out of time, but it is what it is. Okay, so I'll just make this hash map. No, I'll just make this map. Because for JavaScript map, it's actually log n implementation. Is log n access and search. It's actually not O of 1, which is slightly worse lah than if we use hash map. But let's just use map for the sake of it. Okay, so I create this map, and every time I reach a solution, I would record that solution. Okay, so here, every time I reach a solution, I would just record that solution. Okay, so set index to be true. Here, I will set index to be false. Actually, it's quite simple for you to do memoization when you already have a tree solution. Basically, what you do is you create a memo object, and you go find all of the return values, and you just record the return values. Let's see if I have any. Okay, no. I don't know why I keep hearing like Discord notifications. Okay, maybe somebody else is messaging me. Anyways, so I'm setting here, okay? So now I've already recorded. I need to retrieve it some way, right? Like here, when I reach 3, I need to check the memo to see if I already have this number, then I can just return. I don't have to continue to search the tree. Okay? So I can do the checking up top here. So I just check if memo has index, right? Meaning that I've already done this and I already know it's true or false. Then I don't have to search again. I can just retrieve it. Okay, so I can just return memo.get index. Okay, so this is basically it. Let me try to run this. Okay, let's see. True, false. Okay, so if memo.has index, then I will return memo.get. Here I will set to true, and then here I will set to false. Shouldn't be an issue. I think maybe I need to okay, maybe what I need to do is that if the step is equal to 0, maybe I need to do an extra setting, because here in my for loop I start with 1. But to be honest, it shouldn't be an issue, I think. Okay, here I'm creating this map, and I am checking if the map has that index, and if I do have the index, I can just return the value, right? Okay, and then here, if index equals to num.length minus 1, I would just return true. Here I'm recursively checking. Okay, so okay, and if it's true, then I will set it to be true at the memo, and I'll return true. Okay, else I will set it into false, and I will return false. So let me just try this first. Sorry. Okay, nums at index, so I will just check if it's 0 steps. Okay, if it's 0 steps, then I'll return false. But to be honest, I don't think this is the case. Yeah. So this is giving me true. New map. Try to bring this in, because sometimes global variables messes up with the things. Okay, so using this DFS function, I'll check if memo has index, and I'll return memo.getIndex. Okay, and if index equals to the last element, then I'll just return true. Okay, and for step starting with 1 until nums at index, okay, increasing step, I would just recursively check for index plus step, and then I will set the value of index to be true. Okay. Okay, so here there's a return as well. So I think I need to set it here. Okay, so memo.set for this to be true. Okay, let me try this. Okay. So learn from my lesson, right? As I mentioned already just now, if there's any return values, okay, I have to put it in the memo. Okay, so let me just submit this solution and see if it runs. A bit slow here. Okay, in the meantime, yeah, it runs. Okay, so in the meantime, the time complexity and space complexity. So with memoization, the time complexity would be decreased to n times n instead of n to the power of n. Okay, this is because I am actually making the tree into something like a linked list. So it's like one line. Okay. Again, you can go read out the implementation on why this happens and how, right? So for this, you can just search for the time complexity of tree depth first search. Okay, and here you can search for the time complexity of dynamic programming memoization. And for the space complexity here, there's actually this extra data structure, okay, memo, which records like all of the indexes. Okay, so the indexes is m, number of indexes, and the recursion stack could vary according to number of steps. So if you notice, it's actually the same with the bottom-up approach, which is n plus m, but we can change it to max n m as well. This may be a bit hard to wrap your head around, but yeah, you can look around because I'm already late. What time is it now? Yeah, late by 13 minutes. So I hope you guys understood what I said. Memo set index plus step. No, we should be checking. So here, this is not the case because if we look at this, oh, this horrible tree. Let me just try to draw another one real quick. Okay, let's say okay, something like this maybe. Okay, so let's say if I am here, okay, and if I know that the next one gives me a true, right? Then this one will give me a true also, right? Because it's at the same path. So this whole tree would be true, true, and true. So if I know the next one is true, this current one would be true as well. So that's why I'm setting the current one according to if the next one is true. Then here I can recursively set it as well. So I would check, so I will return this true up. So if the next one is true, the current one will be true as well. So that's why here I am checking, okay, I'm checking for the next one. And if the next one is true, meaning that this is the correct path that will reach the end, I will set the current one as true as well. Okay, I hope that you understood what I mentioned here. You know, like trees are really hard for me at first when I first started DSA and Leetcode stuff, right? It was quite of a hard topic for me to wrap my head around, but eventually you get the hang of it, especially with the complexities and stuff and dynamic programming. That's why I really hated the top-down approach because it is very prone to errors. If you use bottom-up, right, it's just like a double for loop and then finish. So I think that personally, I really prefer this tabulation method. And I know that a lot of people that are into like Leetcode questions, right, they prefer tabulation methods also. So if you want to do dynamic programming and you don't know which to start from, you can start with doing tabulation. And this recursion method is for the scenarios where if tabulation is almost impossible, then you can use recursive. I know recursive is like it's a big thing that you have to wrap your head around, but then you get the hang of it slowly but surely. Right, so this is the end of the session. Once again, let me know if you have any feedback, comments, how we can do better or not. I'm thinking that maybe, actually I am thinking, I have not discussed with my team yet, but I'm thinking that maybe if at nights, if you guys are like not free, we can do it once in 2 weeks, but a longer session. So maybe I will make a poll soon for you guys to vote and see which one you like. Because I know now that it's midterm season, that's why there are less people. But, we'll see which one you guys prefer. Also, let me know if you want more difficult questions or easier questions or what type of questions. Just feel free to give me any feedback. And that's it. I hope you learned something from today's session. And we will see you next time. Right. Sammy, you got anything to say?